Okay, right. So for the last few lectures, we've been talking about mean square or L2 convergence of Fourier series, and also talking about some important consequences of the methods that we use to prove this theorem. And in particular, the two very important consequences which we saw were one, an inequality which is known as Bessel's inequality, which I'll review shortly. And two, a very important identity which relates the integral of a function squared, or the so-called L2 norm of the function, to the sum of the squares of its Fourier coefficients, and in particular says that these are both finite, and in fact, either both finite or both infinite, and in fact, if they're both finite, then they're equal to one another, right? So this was a very important result which we illustrated in the last lecture, and looked at a particular application of. And so what I want to do to begin this lecture is just talk about more general versions of these. And so it turns out that we're going to actually use a slightly more general version of the Bessel's inequality later in the lecture to prove our pointwise convergence theorem for Fourier series, which is the next topic that we're turning to after I just go over this a little bit. Right, and so so let me just call this section a more general Fourier, or let me just say more general Bessel inequality. And in the context, or in the scope for it, as we do this, we'll have an opportunity to review what the Bessel's inequality was. Right, and so now we're just going to assume not that we just have, so remember our Fourier series involves sums of complex exponentials with different frequencies, right? And so now we're just going to assume we just have an arbitrary sequence of functions. Well, now let's say we're looking at, say, an interval a to b. So before we were looking at the interval minus pi to pi, it's going to turn out that everything we did kind of works on a more general interval. In fact, let me so we don't stray too much. Let me just continue to consider minus pi to pi, and let me just remark. You can see the formulas in the book that this also works on any AB. With suitable modifications to the definitions of the inner product and the norm. So I'll send you to the book if you if you're interested in these formulas. They're all written out in the textbook. Basically, you just have to change the bounds and the integrals that appear in the norm and the inner product to a to b, rather than minus pi to pi, and maybe change one of the constant terms, and then it's all the same, right? Right, and so we're assuming we have just any sequence of functions on minus pi to pi, but we're also going to assume that we have an orthogonality property, right? So such that if I look at the inner product that we defined previously of two of these functions, that this is equal to 0 when they're distinct, right? So if I have two distinct functions from this list, they're orthogonal. So it turns out that for any such sequence, so this is sometimes called like a sequence, an orthogonal system of functions, or orthogonal sequence of functions. For any such sequence, we have a version of the Bessel inequality. And so the conclusion is that if you look at the sum over n of these functions, and you look at the inner product of any function f squared, right? So for technical reasons, we have to normalize this, divide by the L2 norm of xn squared. That this sum is always less than or equal to the integral from minus pi to pi of your function squared. Right, so this is like 2 pi times the L2 norm of f squared. And so in particular, this could be an infinite sum. And so this also says that if your function f is square integrable, or if this integral is finite, then this series here of these kind of generalized Fourier coefficients that you get by taking the inner product of f with functions in this list is finite and less than or equal to this. I just want to point out, I'm not going to go too much into detail. Again, there are some more details in the textbook. So there's also a more general version of Plancherel's theorem, or sorry, the Parseval theorem. I'm gonna keep mixing up Plancherel and Parseval because a lot of people in my field refer to them refer to both as Plancherel. Although classically the theorem we talked about should be called Parseval theorem. Right. So there's also a more general Parseval theorem of this variety, which tells you that under certain conditions, you can have an equality here. Right. So this is in, I think, section 5.4 in the book. I'm not going to require you to know too much about this. You may have maybe one homework assignment where you use it, but I'll make sure to point out where to go to look up the result if needed. Right, and so this theorem gives you certain conditions on the sequence of functions under which you actually have equality here. So this kind of generalizes the case that we did before, where the xn was en from the previous lectures. It was like e to the inx. This is one example of a system of orthogonal functions. In this case, each of these L2 norms is equal to 2 pi, right? Because the integral of this squared is just the integral of 1 from minus pi to pi, so you get 2 pi. And so there was also like a 1 over 2 pi in this inner product, so those cancel out, and then you get this, right? So this is the result we saw last time. Right, and so what conditions do you need in order to have equality here? Well, you need these xn turn out to have to be, for example, the eigenfunctions for certain boundary conditions, and you have to include all of them, right? And you need some symmetry conditions on the boundary conditions, which are a little technical to go into, but basically all the boundary conditions that we've looked at so far will work. So for example, if you have, like, for example, just cosine Fourier series terms, this will work, I believe. Right. Okay. Right. In any case, this will at least work if your interval is like 0 to pi. Okay. Right. So anyway, I'm not going to go into too much detail about how to prove this more general version, mainly because kind of algebraically or formally, it's basically the same argument that we gave in the last lecture, right? So you look at the difference between f and a certain sum, and you show that you have orthogonality, and using basically the Pythagorean theorem for functions, this kind of pops out of this orthogonality relation. So the proof is basically the same as the proof we already did. So if you want to see this written out, it's also in the textbook, written out in this level of generality in section 5.4. Okay. All right, so now we're going to move on and talk about the next big convergence theorem for Fourier series. And so in particular, we're going to talk about pointwise and uniform convergence for complex Fourier series. And so then in the next lecture, which will be the final lecture about Fourier series, I'll talk about how, right, so all these results, we're proving them all for complex Fourier series. I mentioned previously that you can use these results to conclude similar things about like sine and cosine Fourier series or full Fourier series. And so I'll explain in more detail how to do that in the next lecture. So we'll see how to go from complex to sine and cosine Fourier series, which are in particular relevant for the types of boundary value problems we were looking at. Right, and so here we're gonna look at the following question, which is a very hard question, which mathematicians have been studying for a long time. We're not going to provide the most general answer to the question, but we will provide hopefully a satisfactory answer that applies for a lot of functions. So the question is, like, suppose, like, say, f of x is a function on, say, minus pi to pi, and we define the Fourier coefficient for kind of to match the common notation, I'm going to write this for the Fourier coefficient. So say f hat, usually we call this like an f hat. This is standard notation for like the nth Fourier coefficient, which we usually call Cn. Right, and so suppose this is my nth Fourier coefficient, nth complex Fourier coefficient, and suppose that we define the sequence of partial sums, which I'll call Sn of x, which is going to be the sum from minus n to n of the Fourier coefficient and Fourier coefficient times e to the inx. Right, so these are the partial sums of the Fourier series. Right, so the capital nth partial sum of the Fourier series for f. And so the question is, when does this series here converge pointwise to the original function? Right, so under what conditions on f? On f, does this series here converge to f of x pointwise? Right, so this is the question that we're going to be addressing today in the lecture. We're not going to give the most general conditions, but we'll find one condition which applies to a lot of functions. Right, and so in particular, right, what does it mean to have pointwise convergence? Remember, let's write out the definition. So the question really is, when does, right, so in pointwise convergence, we're looking at the difference of Sn of x minus f of x, right? And for a particular point x that's been fixed. And so the question is, when does this converge to 0 as n goes to infinity? So maybe more precisely, what do we need to assume about the function f for this to be true, right? So for which type of f, or which functions f, does this limit go to 0, right? And so remember, this is of course just the statement that the partial sums of the Fourier series, which are up here, converge pointwise to the function f in the sense we defined a few lectures ago, right? Right, and so we'll see how to do this. And so let me actually just state the theorem now, which we'll be proving. And then time permitting, we'll also talk about uniform convergence at the end of this lecture. And if we run out of time, we'll continue talking about uniform convergence in the next lecture. And so the theorem is the following. So this is our pointwise convergence theorem. And so the theorem is, suppose that the function f is differentiable on the interval, say, minus pi to pi, not including the endpoints. Of course, if you're just looking at a finite interval, it doesn't make sense to talk about differentiability at the endpoints anyway, because you need left and right limits for differentiability. Right, so suppose it's differentiable in the interior of this domain, and also suppose that the derivative is continuous on this domain. Then the conclusion is that we have pointwise convergence, right? So then the partial sums of the Fourier series, the difference of Sn minus f with this definition up here, again, partial sums of the Fourier series, this converges to 0 as n goes to infinity for each x between minus pi and pi. Right. And so this is the pointwise convergence result, right? So for each point between minus pi and pi, we have this limit this difference converging to 0, which is equivalent to saying that the partial sums converge pointwise to the function f. So I just want to point out that this does not include the endpoints, and this is very important. If you want convergence at the endpoints, you need some more hypotheses. We'll talk a little bit about this when we talk about uniform convergence, and also a little bit more in the next lecture. But it's very important to remember that this is only in the interior. And indeed, there are lots of examples of functions for which you'll have convergence, like the pointwise convergence inside the interval, but as soon as you hit one of the endpoints, the convergence fails at those points, right? So it's very important to point this out. Right. And so, right, so maybe just one more quick thing to write down, and then we'll proceed with the proof. Right, I mean, oh, sorry, this basically just says that if you take the limit as n goes to infinity of the partial sums, that we indeed have like kind of this identity we were assuming earlier when we were working with boundary value problems, that the function f is indeed equal to its Fourier series pointwise. Right, and so I mean, this limit here, really, we mean sending both to infinity. This is the same thing as writing this, right? So f is equal to its Fourier series pointwise. Right. Possibly this may not converge uniformly, meaning the rate that the series converges to the function could depend on the point, but we at least have that it eventually converges. Now you may be thinking, okay, this is very technical. Like, why do we need to worry about uniform convergence? Maybe pointwise convergence is enough. Well, if you think about this in terms of application, I mean, what you're going to be doing typically is you'll take some finite, assuming you know it converges to your function, you're going to take some finite truncation of this, and that will approximate your function, presumably, right? If this converges to f, then the difference is going to be small, so it'll give you an approximation. The issue, though, is that the quality of that approximation, if your convergence is not uniform, could depend on the particular point you're looking at. And so there could be some points in your domain where your approximation is really bad, but you don't know that it's bad, right? And so this is why it helps to know if your function converges uniformly, right? So if we have a stronger uniform convergence, we know that kind of the rate of convergence everywhere will be about the same. Pointwise convergence may not be sufficient in some cases because it may take a long time for some points for it to converge, whereas other points it's not taking a long time to converge, right? And so you may take like a truncation like from -1,000 to 1,000, and at some points you'll think this is giving you a good idea of what the function looks like, and it may be true, but at other points it may not be if you don't have uniform. Right, but in any case, this is still a good starting point. So again, we'll talk more about uniform convergence later. Let's begin just by focusing on this pointwise result. Right, okay, and so let's begin the proof. So this is not going to be a short proof. It's probably going to take most of the rest of the lecture, but I think a lot of the ideas and concepts that we use to prove this are important, so it's worth going through this. And so in particular, we're gonna use some ideas which you've been thinking about on the last few homework assignments, which will help us in the proof. And so this is one of the reasons why I gave some of these things to you as problems, because now we're going to use them to prove this theorem. Right. Okay, and so right, so let's begin with this. And so this proof involves, of course, it involves looking at this difference. Right, we're going to assume, right, say x is fixed. We're just going to fix a point in the interior of the domain, right? And we're also going to assume that this function f is fixed, right? And so for this particular function and this choice of x, we need to show that this difference here will converge to 0. If you try to just show this directly, it's not really clear how to proceed, right? And so what we're going to do is use a very clever idea, which involves writing this difference as a certain integral, which is easier to estimate. And so in order to do that, we're first going to begin just by looking at the sequence of partial sums, right? And so we're first going to look at this thing here. Right. Okay, and so in order to analyze this object, it helps to introduce, oh, sorry, this shouldn't be negative. It helps to introduce a very important function for Fourier series, which is called the Dirichlet kernel. And so you're already a little bit familiar with this this function because you looked at it in homework, I believe homework 8. And so we're going to define a new function kn of x, which is going to be the sum from minus n to n of just e to the in x, right? So like we're taking all the Fourier coefficients between minus n and n to be 1, and then the other Fourier coefficients will be 0 outside of that range, right? Well, in homework 8, we proved that there's a nice analytic representation of this in terms of sine, a ratio of 2 sine functions, right? So we proved in this homework that kn of x is equal to sine of n plus 1/2 x divided by sine of x over 2, right? And so we're going to use this fact to make the proof work. So in order to understand how we're actually going to use this, we just need to make a few preliminary observations. The first point is that, right, let me just write this as some preliminary. Let me spell this right. Okay. And these are relating to, these observations will relate to what are the Fourier coefficients of these two functions, right? We already said verbally what the Fourier coefficients of the partial sums are. I'll write it down also in a minute. And what are the Fourier coefficients of this function? Right, and so the first observation is that, well, let's say I look at this Dirichlet kernel, and I look at the nth Fourier coefficient. Right. So this is kind of why I introduced this new notation for Fourier coefficients. It's kind of more compact, and it tells, since we're working with different functions and different coefficients of different functions, it helps to remind yourself what the function is, right? So this is one reason why I introduced this new notation and why people usually use this notation for Fourier coefficients. Right, and so the question is, well, what is the nth Fourier coefficient of this function here with n fixed, right? Well, you can just read them off, right? So this is given to you as a Fourier series. So this is like the definition of our function. And so the coefficients are just going to be 1 between minus n and n and 0 outside of that range, right? Right. On the other hand, let's look now at the Fourier coefficients of our the partial sum for the Fourier series for f. Right, if we come back here, we'll see that, well, they're not equal to 1 between minus n and n, they're equal to f hat of n, but they're also equal to 0 outside of this range. So these are equal to f hat of n if n is between minus capital N and plus capital N and 0 otherwise, right? And so what I'm going to do is claim that I can write using these two observations. I mean, the Fourier coefficients seem pretty similar, except I have a 1 here rather than an f hat, or f hat, an Fourier coefficient of f here. And so the claim is that I can write the nth partial sums as a convolution of the Dirichlet kernel with my function f, right? And so what is a convolution? Remember, this definition was introduced in the last homework assignment. right? Where we, right, so remember this is equal to an integral 1 over 2 pi minus pi to pi of like f of y times kn, or let me rewrite this the other way, sorry. F of x minus y times kn of y dy, right? So this star here is a certain operation on two functions, which is defined this way. And hopefully you've already thought about this on homework 9. And so this is called convolution. Right? Right, and so why is this true? Well, recall that you proved on homework 9 that if I have a function, if I have a convolution of two functions, and you take the nth Fourier coefficient of this function, then this is equal to the nth Fourier coefficient of f times the nth Fourier coefficient of g, right? So this means that if you take the convolution of two functions like this, the Fourier coefficient of this new function which you formed is just the product of the two individual coefficients, the nth Fourier coefficient, right? So in the side of the Fourier coefficients, multiplying things together is like convolving the functions, right? In the non-Fourier side of things. Right, and so well now let's apply this identity to this, right? So note that therefore, well, if I take the Fourier coefficient of kn convolved with f, say the nth Fourier coefficient, this has to equal nth Fourier coefficient of kn times the nth Fourier coefficient of f, because this is a convolution, right? So we're just using this identity which you proved in homework 9. And well, what is this here, right? Well, this is equal to 1 in a certain range, right? So we already saw in the preliminary observation above that this is 1 if n is between minus capital N and capital N and 0 otherwise, right? And so if we use this fact, we see that this is equal to, well, if n is between minus capital N and capital N, it's not equal, this is equal to 1, right? So but then I have 1 times f hat n. So it's equal to f hat n, or the nth Fourier coefficient of f. On the other hand, if n is outside this region, we just get 0. Right? But this is exactly what we had up here, right? So this is just equal to the Fourier coefficient of the partial sums at n, right? So we have this fact. And so what this means is that these two functions have the same Fourier coefficients, right? And so the question is, well, if these two functions, I'm trying to show that they're equal. We haven't quite shown that they're equal, but we've shown that these two things have the same Fourier coefficients. Well, if two functions have the same Fourier coefficients, do they have to be equal? The answer turns out to be yes, at least in this context. Right, and so this will be on your next homework. It's actually a relatively short proof, which you can do using some of the stuff we talked about in the previous lecture. In particular, using the Parseval theorem is one way to show this. So if, say, if two functions have the same Fourier coefficients for all n, and you need this to be true for all n, not for some n, then the functions have to be the same. Right, and so this is kind of like a uniqueness result for Fourier coefficients, right? So the Fourier coefficients uniquely determine the function. And so again, this will be on the next homework with maybe a hint or two about how to do this. And so if we apply this result, well, we just showed the Fourier coefficients are the same. And so this proves this identity, right? Okay, and so what we're going to do now is, again, it may not be clear why we're doing this, but hopefully you'll see the punchline shortly. It's going to turn out that because we writing our partial sums in this way will help us prove the pointwise convergence. And so now let's come back. We're trying to look at the difference here. So I'm going to plug in this new identity we have for the partial sums into this difference, right? And so now let's proceed. Right, we kind of have all the tools we need at this point, and so we can kind of dive into the more complete argument. So now we have, from what we just saw, Sn of x minus f of x is equal to convolution of this Dirichlet kernel with f, right? We're replacing the partial sums by this minus the function f. And so I can write this now as 1 over 2 pi integral minus pi to pi of kn of x minus, or actually kn, let me replace, I'm writing this in the wrong way, sorry. F of x minus y times kn of y dy minus f of x, right? And so here I plugged in plugged in this identity we just proved, and then I plugged in the definition for convolution here, and we're just leaving this alone. And now we're going to use a very important trick, which shows up all the time in these types of arguments. Right. And so if you take away one idea from this proof, this should be one or two ideas from the proof. This should definitely be one of them. The other should probably be writing the partial sum as this convolution, which is really, it's going to be related to this trick anyway. And so the trick is, well, first note that if I look at the integral of kn of y dy, like now we're forgetting that there's an f here. Let's say I look at this integral from 1 over 2 pi times minus pi to pi. Well, this is equal to 1 over 2 pi by definition times the sum from minus n to n of minus pi to pi e to the inx dx, right? But these are all 0 except when n is equal to 0, right? Because the integral of e to the inx from minus pi to pi is equal to 0 if n is not 0, as we've seen before. So this is just equal to, so these are 0 if n doesn't equal 0. And so this is just equal to 1 over 2 pi times integral minus pi to pi of e to the 0, which is just 1, right? Because e to the 0 is equal to 1. And so when I put a 1 here, I just get the length of this interval, which is pi minus pi, or 2 pi. And so I get 2 pi divided by 2 pi, which is 1, right? And so this says that this integral is equal to 1, right? So that's the proof. And so I can write f of x as f of x times 1. And now this is the very important trick. I'm going to replace 1 by this integral here, right? Because 1 is equal to this. So this is equal to f of x times 1 over 2 pi integral minus pi to pi of kn of y dy, right? And so now notice this doesn't depend on y, so I'm going to bring it inside the integral, right? So I'm going to write f of x as 1 over 2 pi times integral from minus pi to pi of f of x times kn of y dy, right? And so this is the very important trick which I was talking about. It heavily relies on the fact that this integral is 1, and that this depends on another point, right? So this depends on x, not the variable of integration. And so now what I'm going to do is come up here and plug this identity in for f, right? And so if I plug this in, we get Sn of x minus f of x. This is the thing we're trying to show is equal to 0, or converging to 0, sorry. So this is equal to 1 over 2 pi times this first integral, which was the convolution, minus this new integral 1 over 2 pi minus pi to pi of f of x times kn of y dy, right? But now we can use the fact that if you're integrating over the same domain, you can combine them, right? Or using linearity of the integral. And so we get this is equal to 1 over 2 pi integral minus pi to pi of f of x minus y minus f of x times kn of y dy, right? So, right. And now finally, we're going to remember up here, we have this result from your last homework assignment. We're going to plug in this formula for kn because it turns out that this formula will be easier to work with in the integral, that which we now have to estimate. And so we finally arrive at this representation of the thing we're trying to show converges to 0. This is equal to 1 over 2 pi times integral from minus pi to pi of f of x minus y minus f of x times sine of n plus 1/2. Well, we're plugging it in with y rather than x, so this should be a y divided by sine of y over 2 dy. Right, and so now, right, we're going to take absolute values. And so now we want to show that this converges to 0. So notice we haven't actually taken any limits yet, right? What we've done is some pretty sophisticated analysis that allows us to rewrite this difference in what will turn out to be a more convenient form, right? If you tried to take a limit here directly, you would have no idea what to do. But here we have these sine functions, which we can actually explicitly work with because we know various things about sines. And we also have a difference of f here. So this looks kind of like a difference quotient for a derivative, right? And so this is kind of why you would think maybe f being differentiable will be relevant, which is what we're assuming it is, right? Okay. Okay, and so now what I'm going to do is actually rewrite this, right? So the goal is to show that this integral converges to 0. We're going to rewrite it in one more way. I mean, there's a lot of reductions here, but this is kind of how these arguments work. Right, so this is going to be 1 over 2 pi, integral minus pi to pi. I'm going to move the sine term over, and so I'm going to have a new function here, f of x minus y minus f of x divided by sine of y over 2 times sine of n plus 1/2 y dy, right? And so I'm going to call this whole thing here, we're assuming now that x is fixed. So I'm going to call this whole thing here g of y, right, for now, right? And so g of y includes everything in the blue brackets here, right? And so now I can write this as absolute value of 1 over 2 pi integral minus pi to pi of this function g of y. Notice this function also depends on x, but I'm assuming x is fixed, so I'm going to omit it from the notation for now. Let me use. Right, so again, g of y is this function here, times sine of n plus 1/2 y dy. Right. And so at this point, we're going to finally use the Bessel inequality that I talked about at the beginning of the lecture. And so I'm going to write this as a fact, which you can check. So let me define x sub n is equal to sine n plus 1/2 y on this interval. So the fact is that these are orthogonal, right? So if I look at xn comma xm, this is equal to 0 if n does not equal m, right? So we have orthogonality, right? And so, right, so this is true. I'm not going to prove it now, but maybe what you should do is maybe pause the video and check. There are a few ways to do this. For example, you could convert this to complex exponentials, or maybe you could use a trig identity, or maybe change variables, and you can show this. It'll be similar to some of the orthogonality arguments we had for the sine and cosine terms that showed up when we were looking at sine and cosine Fourier series. If you want to see the details, I'd be happy to also do this in the Zoom meeting to check this, right? Okay, well, assuming that this is the case, which it is, well, that means that this Bessel inequality applies, right? It may not be immediately clear how it's going to apply to help us solve this problem, but I'll talk about that in a second, right? I mean, actually, well, let me talk about that first, right? So notice that this is an inner product, right? In particular, we can write this integral, let me call it star, as the inner product of this function g with xn, where xn of y is again the sine function, right? And so what we're really trying to show is that these inner products converge to 0, right? So we want to show that the lim as n goes to infinity of these things is equal to 0, right? And that would suffice because it would prove, remember, this is just equal to this difference, and we're trying to show this difference is 0. And so, right, so I'm just kind of rewriting the thing we're trying to show in this way. Notice that the function g depends on the point x, right? So for a different point x, we're going to get a different function g, but I just wanted to kind of not clutter the notation too much, which is why I don't have it written here, right? Well, recall from the Bessel inequality states the following. So if we know that the L2 norm of g is finite, which in this case is a non-trivial thing, right? Because this function g is kind of complicated. So it may not be true that this has a finite L2 norm. And indeed, we're going to have to prove that as the final step. But if this is the case, then the sum of these inner products squared over all n has to be finite. And in particular, it has to be smaller than some constant times this L2 norm. And so it has to be less than infinity, right? You may think, okay, well, why is this relevant here? But remember, this is now just a sum of numbers that are positive, right? And so the only way an infinite sum of positive numbers can converge is if the limit of the terms go to 0, right? Right, so this converges. So the limit as n goes to infinity of each of the terms has to be 0. Right, otherwise it wouldn't converge, right? So this is like it's not necessarily the case that if these go to 0, then the series converges, but if the series converge, then the terms have to go to 0, right? Okay, but if the limit of the square goes to 0, then the original also has to converge. The limit of the power 1 also has to converge to 0, right? And so this would imply that, well, this is what we're trying to show is 0, right? This would imply this is 0. And so therefore, the partial sum would converge to f, right? So it would imply that the partial sums of the Fourier series of f converge to f at this point, right? And so what this shows is that because of this Bessel inequality and because of this observation that I just made, all we have to do now is check that this L2 norm of g is finite, and then we'll be done, right? Because then you just follow this argument, L2 norm is finite, this infinite series has to converge, the only way the infinite series can converge is if these inner products converge to 0, because these are what you're summing. But these are just equal to the difference of the partial sum in F. And so the original thing had to converge to 0, right? Right, so this is, of course, like a very elaborate argument, which was worked on over several decades or longer by different mathematicians who simplified other arguments, right? So this is not something that, unless they were a genius, someone would like immediately come up with, right? So you shouldn't be worried if this seems kind of complicated, because it is, right? But hopefully I'm presenting it in a digestible way. Right, and so finally, we need to prove that the final thing that's missing we need to prove that this that this L2 norm is finite, right? And this, remember, this depends on the point that we were picking, right? And so the size of this may be different depending on the point, right? Right, and so now let's remind ourselves what this is, right? So this is equal to 1 over 2 pi times integral from minus pi to pi of f of x minus y minus f of x over sine of right, sine of y over 2, excuse me, squared dy, right? Just plugging in our definition for g, which was up here, right? But we're just looking at the square of this, right? And so what we want to do now is show that this integral is finite, right? And so here we're going to use the hypotheses on our function, right? So notice that actually up until this point, we haven't used anything about the function f. And so the argument up until this point works for any function. But now we will use hypotheses on the function. In particular, that f prime exists and is continuous, right? Which is very important. Okay, sorry, that handwriting was terrible. Let me rewrite that. Right. Where is the derivative going to enter the picture? Well, you can see this difference quotient here. So this kind of indicates where the derivative will show up. Right. Oh, sorry, I'm actually realizing I left out, oh, sorry. I left out one minor point. So let's come back to the Bessel inequality up here. Right, notice you had to divide by this term here, right? And so which is basically the L2 norm of xn, right? And so if I come back to what I wrote, this really should have been divided by L2 norm of xn, right? But you can show that this is equal to, I believe, 1/2, right? And so this is just, I mean, this is just, what is this xn? This xn is just sine of n plus 1/2 y squared. And so this is very similar to some other integrals we've done. In particular, when we were looking at sine and cosine Fourier coefficients, we proved something very similar, that if you square this, the integral doesn't depend on n, right? And so you just get some number. And so that gets absorbed into this constant here, right? So sorry, I should have pointed that out. I forgot to mention that. Of course, the argument, assuming that the argument is exactly what I said, right? Okay, and anyway, so coming back to where we were, right? So this is the square of our function g, and we want to show this integral is finite. And so what we're going to do is try to make the derivative of f appear, right? We're assuming something about the derivative. Let's try to make it appear here. So this is equal to 1 over 2 pi times integral minus pi to pi of, well, I have f of x minus y minus f of x notice that the difference between these 2 points in absolute value is just y, right? And so in order to make a difference quotient appear, let me just put a y in the denominator, right? In order to match up with what I have to put another y in the numerator here, and then I have the sine term. Right? And so I've just rewritten my integral. We'll notice that since f is differentiable, this whole thing is, the f is of course going to be bounded, right? And so the only situation where this thing is problematic in terms of this being finite is near the origin, right? Where we're dividing by 0. Right, but if I'm not gonna go through the full rigorous detail here, but let me indicate the main points. If y is basically 0, this quotient is just going to be basically the derivative at f, right? Because remember that the derivative at x, sorry, did I say derivative at f? I meant derivative of f at x. Remember, the f prime at x is basically the limit of this difference quotient as y converges to 0, right? And so if y is very close to 0, this whole ratio is basically going to be f prime at x. But we're assuming that f prime is continuous, right? So since f prime is continuous, it has to be bounded. By some uniform constant c. Right. Remember, if you have a continuous function on a finite domain, it has to attain a maximum value. Well, f prime is continuous, and so there's some maximum value which doesn't depend on x, right? And so that means that this whole ratio is bounded by this number, right? Near 0, right? On the other hand, if you're away from 0, there's no issue with this being finite, right? Because f is continuous and then there's no singularity here. So this is also bounded by some constant c away from 0. And so therefore this term is okay, right? So this term here is just bounded by some constant, right? And so it remains to show that this term is also bounded by some constant. Once again, the only issue is, I guess, near 0, right? Because, well, when is sine equal to 0? It's equal to 0 at the origin and also at integer multiples of pi, but there's no integer multiple of pi other than the origin on this domain. And so the only issue where this may not be finite is in the origin. But you can show using L'Hopital's rule that this is also bounded. So I'm going to skip those details, but you can show using L'Hopital's rule that this term is also bounded. Right. And so it turns out that both of these terms here, I can uniformly control them by some constant, like some large number, which could depend on the function. And it has to depend on the function because it depends on the derivative of f, but it doesn't depend on the point x, right? And so since both of these terms in the integral are smaller than some constant that doesn't depend on x or y, this integral is finite, right? Right. Right, it's less than or equal to 1 over 2 pi, integral minus pi to pi. Both of the terms here, we just explained why they're bounded by some number. So bounded by some constant, which is finite, right? The good news for us is we don't need to know what this constant is. We just needed to show that it was finite, right? So that's a little bit easier than actually calculating it. And so that's what we did. And so then tracing this back, well, following this argument here, we're done, right? So this completes the proof. Right. And so that proves our big pointwise convergence theorem. Remember, the key hypothesis was that the function f has to be differentiable on the domain and the derivative has to be continuous, right? And so we use both of these hypotheses in exactly this step here. It's worth pointing out, though, that the pointwise convergence theorem is true whenever this quantity is finite, right? So you may not need your function to be differentiable if you can prove using a different argument that this thing is finite, but in general, that's going to be pretty hard to show, right? So this is maybe the easiest hypothesis which will allow us to prove this. Right, and so there are some other small extensions of this which are important, which I'll talk about, not this lecture, but at the end of next lecture. So maybe we'll come back to that point, and I'll say a little bit about this. Right, and also we'll have an opportunity in the next lecture to look at some examples. Right, so you may want to see some examples. I'll leave a lot of time in the next lecture to do this. Right, today I just want to focus on these two main theorems. Right. Okay, and so this is it for pointwise convergence. And so now what we want to do is move on and talk about uniform convergence. Right. So it's not it for pointwise convergence, but that's kind of our main result. And there's another related result, which, as I just said, we'll talk about more next time. Okay. Okay, and so of course uniform convergence is typically harder to prove than pointwise convergence. And so we're going to need a little bit more of some more hypotheses in order for this to work. And so the following will be our uniform convergence theorem for Fourier series. And so in this case, we're going to suppose that our function f is differentiable and is continuous as before in the domain. And we're also going to assume that the function has periodic boundary conditions, meaning f of pi is equal to f of minus pi. Right, so these are periodic boundary conditions. Right, and so this is kind of the big distinguishing feature from the last theorem. We did not assume this in the last theorem, right? The only issue was that the last theorem, you may not have pointwise convergence at the endpoints, and this turns out to be related to a failure of uniform convergence in some sense, which again we'll talk about more next time. But if you assume that the function has these periodic boundary conditions, you can actually improve the last result to get uniform convergence. Right, so this is like you're like kind of a 2 pi periodic condition. Basically means that if you take this function f, which we're only assuming is defined on this interval, and you look at the periodic extension to the rest of the real line in this, which we defined a few lectures ago, then the periodic extension is continuous. Right, that's what this condition ensures. And right, you also need the hypotheses from before, which are that the derivative exists and is continuous. Right. Right, and so how are we going to prove this? We're also going to use another result from your homework, which is from the homework this week, homework 9, which is this result related to uniform convergence, and I'll say a little bit more about that soon. But let me just kind of sketch the idea, and then we'll fill in the details. And so the idea is to look at how fast the Fourier coefficients of the function decay. Oh, wait, sorry. I'm just realizing now that I didn't even state the rest of the theorem, excuse me. So under these hypotheses, then the partial sums will converge uniformly to f. So if I look at the maximum from minus pi to pi of so these are the nth partial sums of the Fourier series we were looking at before. You don't just have pointwise convergence, but you have uniform convergence as n goes to infinity. Right, and so this is the partial sums of the Fourier series converge uniformly to f, right? And so the infinite sum is equal to f, but it converges not just pointwise, but in the uniform sense, right? Right, and so the idea of the argument is to look at the decay rate of the Fourier coefficients. And we're going to see that under these hypotheses, with the derivative existing and also these periodic conditions, we can show that the Fourier coefficients have to decay at a certain rate. And this is going to allow us to apply this convergence test from your more recent homework to obtain uniform convergence. Right, and so let's do this. Right, and so there's a preliminary results which we're going to use, which I'll call a theorem, a different theorem. And so this actually relates the Fourier coefficient of f to the Fourier coefficient of its derivative. And once we prove this result, we'll be able to prove the uniform convergence theorem, and then we'll be done for the day. Right, and so the theorem is the following. Let's look at f prime, and let this be the nth Fourier coefficient of the derivative of f. Using the same notation from before. The theorem is that this is equal to 2 pi I n times the Fourier coefficient of f, right? And so why is this true? Well, this is basically just integrating by parts, but we have to use the periodic condition, right? So if f of pi is equal to f of minus pi. And so this is kind of one of the key points in the argument where this condition here actually plays a role, is in order to have this result. Right. And so, right, and so this is actually another point where we're going to be using a very important idea. So note that I can always write e to the minus inx, which is this term that appears in the formula for the Fourier coefficient. I can write this as 2 pi I n, or sorry, I'm copying the wrong formula. I can write this as minus 1 over in times the derivative of the same thing, right? Because the derivative of this thing is just minus in times itself, right? And so if I just divide out by that constant, I just recover the original thing, right? And so what we're going to do is we're going to plug this formula in for the exponential in the definition of the Fourier coefficient, and then we're going to integrate by parts, and we'll see that this will come directly from that, right? And so this tells me that if I take the nth Fourier coefficient, well, by definition, this is 1 over 2 pi integral minus pi to pi f of x e to the minus inx dx. Let me now plug this in. We see that this is equal to minus 1 over 2 pi in integral minus pi to pi of f of x times the derivative. Right. And so now what I'm going to do is integrate by parts. So this is my dv, and this is like my u for integrating by parts. And so my du is just the derivative of f, which is f prime, and my v is just e to the minus inx, right? And so if I write out the integration by parts, we're going to end up with 1 over 2 pi. I mean, let me factor out this whole constant here, right? So this is like minus 1 over 2 pi I n. And then in brackets, we're going to have the boundary terms, which are like u times v, looking at the difference on the boundary, right? So that's f of x e to the minus inx from minus pi to pi, and then minus the integral from minus pi to pi of f prime, which is du times v, which is e to the minus inx dx. Right. Okay, well, what is the first term here, which involves the boundary terms? This is equal to f of pi e to the minus in pi minus f of minus pi times e to the minus in minus pi. But we're assuming that f of pi is equal to f of minus pi. And we also know that this exponential is also 2 pi periodic. Right, so if you look at e to the minus in pi, right, this is equal to e to the minus in, or just equal to e to the in pi, or e to the minus in minus pi. One way to check this is to just use the Euler formula, right? So write this as cosine of n pi plus sine of n pi, something like this. I sine of n pi, sorry. And you can just check that this is true. And so these two things are both equal, right? So both of these functions satisfy the periodic boundary conditions. So this is just equal to 0, right? And so this whole thing is 0. And so we end up with f hat of n is equal to, well, here we have minus 1 over 2 pi in. The minus sign will cancel, so we'll just plus, and then times integral minus pi to pi of f prime of x times e to the minus in x dx, right? And so, well, this thing here looks a lot like the Fourier coefficient, right? In particular, let me factor out 1 over in, and then I have 1 over 2 pi times this integral. But this integral is just the Fourier coefficient of f hat, or sorry, of f prime, excuse me, right? So this is 1 over in times f prime hat, right? And so that's the formula that we claimed. I think I accidentally put a 2 pi in here, right? So that 2 pi shouldn't have been there, excuse me. Right, so we get the Fourier coefficient of f prime is in times the Fourier coefficient of f, right? Right, so this implies Fourier coefficient of f prime is in times Fourier coefficient of f, and that completes the proof. And so now we're gonna use this to prove the uniform convergence theorem with one additional tool, which I guess I have to add on. Right, and so this final tool is right. Sorry, I'm just trying to decide very quickly if I want to do this all now. And right, so I think we can do it, and without going too much over time. Right, and so let's proceed now with the proof of the main theorem, uniform convergence theorem. Using this result, which will be very important. Okay, and so we're going to use the following theorem, which you proved on the most recent homework assignment. Right, so suppose suppose this converges pointwise. Actually, this is what I'll do. Sorry that so it's a lot of material, so I never know exactly how much I can cover in a reasonable time frame. What I'll do is state this result and explain why it's true, and then in the next lecture we'll begin by completing the proof of uniform convergence, which will just take like another 10 minutes, and then I'll talk about the other stuff which I mentioned before. Right, and so the theorem is the following. So let's suppose that our sequence of partial sums converge pointwise. And also, right, so we know some conditions under when this is the case. In particular, if f prime exists and is continuous. So this is what we have up here, right? We're assuming this in addition to this extra 2 pi periodic condition, which allowed us to use this result or prove this result here. Right. So let's suppose that we know the partial sums converge pointwise, which we do for this function. And also that if I sum the absolute values of the coefficients, not the absolute value squared, but the absolute values, right? So again, we're assuming the Fourier series converges pointwise, and we're assuming that if I sum the absolute values of the coefficients, then that's finite. Now, this is not always going to be true, right? You need extra conditions for this to be true, but we're assuming for now that it is. Then the conclusion is that the sum converges uniformly. Right, and so this should remind you of, again, this result on your most recent homework assignment. And so the proof, which will use that result, right? I'm not going to reprove the homework problem, but the proof is the following. Well, let me call an the absolute value of the Fourier coefficient. And so we have that the sum of an, or just an, is finite. Right. Moreover, if I come back over here, the terms that I'm summing, if I look at this absolute value, this is always less than or equal to an, right? Just kind of trivially, because the absolute value of the complex exponential is always equal to 1, right? Because right, this is like you can just see from the formula, the Euler identity, for example, that this is equal to 1 in absolute value. And so in fact, this is actually just equal to, it's not even less than or equal to, it's just equal to this an when I take the absolute value. And so, well, these are the hypotheses for this result on our last homework. So this is problem 4 on homework 9. Right. And so we proved in that homework assignment that under these conditions, right, so you have a sequence of partial sums, not necessarily for a Fourier series, but we're applying it for a Fourier series in this case, where the functions here are all uniformly bounded by some sequence, say an, and moreover that sequence is finite, then the series has to converge uniformly. Right, so it just follows from this. Problem. Right, so in that problem, again, we concluded that under these hypotheses, the series has to converge uniformly. Well, we know the hypotheses hold because we're assuming that this sum is finite, right? And so what this tells us then is that if we have a sequence of partial sums of a Fourier series, which we know converge pointwise, for example, in the context of this theorem, we're assuming f prime exists and is continuous. So by the first theorem that we proved today, the Fourier series converges pointwise. So that satisfies the first condition. If we additionally know that this sum, the sum of the absolute value of the Fourier coefficients is finite, then we can use this exercise that we did to conclude that it actually has to converge uniformly, which is stronger. And so the way the proof is going to work now is we're going to show that this sum is finite under the hypotheses. And so in order to do this, we're going to use this result here, which relates the absolute value of f to 1 over n times absolute value of f prime hat, or sorry, absolute value of Fourier coefficients of f to 1 over n times absolute value of the Fourier coefficients of the derivative of f. And so we'll use this as kind of the key tool to make this work, plus another inequality, which is a famous inequality, which I'll introduce next time. And then we'll be done with the convergence theorems. Right, and then the last part of the next lecture, as I mentioned a few times, we'll talk some examples, go through some examples so you can see this stuff in action. And then we're going to pause a little bit for an exam, and after that, I mean, there will be one lecture before the exam, but sort of the next and final block of the course will be about Laplace's equation, or these things called harmonic functions in like 2 dimensions. And so Fourier series will not go away because we're going to have to use Fourier series techniques to understand solutions to this equation as well. But we are going to be kind of moving on after the next lecture.